Hello, we are here for one more lesson of this T-FLEX analysis training course, and the topic for today will be the construction of the mesh. The mesh, we already spoke about it, is the fundamental step and element when we talk about finite element analysis, because the mesh defines the mathematical model that allows the software to make all the necessary calculations independent of the type of calculations we need. We've seen already a couple of times in the videos how to create a mesh, so it's very easy. Basically, analysis menu, we need to create a new study. So finite element analysis study. We will define the body, confirm, and the mesh will be automatically calculated because after defining the body, we go to this dialog box where we make all the definition of the mesh, and it is the center topic for today's lesson. There are a couple of interesting points. Most of these, it's also important to have some experience with different modules, with different examples. It helps. But there are a couple of parameters among all of these that are important, and we need to look on them. The first important notion is that we can have several types of meshes, and we can go through them through this option. So tetrahedrons or curvilinear tetrahedrons. And the main difference that we can have in these different type of elements is that the curvilinear type of mesh, it's more suitable for curvilinear geometry. The setback that we have in this curvilinear is that we will create more points, we'll have a heavier mathematical mesh and model, and it will take more time to make the necessary calculations. On the other hand, the straight edges finite element has nodes only on the vertices, and it's a lighter model. It is important to notice, and this is a general rule, that a heavier mesh will lead to more accurate results, thinking that we have more points in geometry that creates a better definition of this geometry. Anyway, there are cases where the straight edge elements, if we have a very small a very small size for these linear elements, it's enough to have an accurate result. And on the other hand, if we have only curvilinear and we have a very small size, which creates a very heavy model, we can go on the direction that maybe it is impossible to make the calculation because the model is so heavy and so dense that we cannot make the calculation. So the idea today is to create a couple of examples so that we can see what to do with this. So for now, I will create this tetrahedron element, and I will put a big value on this. So let us create a couple of modules. Every time we create some conditions, the model is calculated and we have the mesh displayed with the result. So let us change now these parameters. So you see number of finite elements 207. So I have the tetrahedrons, and you see that in this area here, this is very rough. So for sure, the result will not be good. Let us change to curvilinear, and I would expect a little improvement on this area. Okay, so you see we have a little more elements and the improvement was good, and the number of elements, it's not much more because we came from 207 to 226. So this is the first item to notice. Okay, it is very important to understand what we have in either of these elements. We can try the prism also, and you see the prism, this mesh, it's not very good, even that we have more elements. So this is one of the cases where more elements do not lead to better results. So let us go back again to curvilinear, and we get to the result. Now we can lead to something that is the mesh size. So we have 1 millimeter, and for sure if we reduce this value, let's say 0.5, we have a little more element. In this particular case, not much. Let us reduce a little more. So you see, if I decrease the value, I get more elements, I get a better definition, and again, better definition, it's better results. So one of the factors, it is mesh size, small value, better definition. Then we have, and I will go back to the basic one. Then we have this item here that is mesh size relative or absolute. So relative is what we use by default, and on the relative it is taken care, or the model, it is the size of the edge is defined as a fraction of the model outlining box longest side. Okay, when we have the relative, and this is the result. Let us leave one unit and let us change to absolute, and we will see the difference. When we have the absolute parameter, the specified size is adjusted, and the definition is regarding the model units. So I expect a much heavier mesh, and you see that it's taking a lot of time to calculate the mesh, so we should have a very small size mesh. It's taking long. Let us wait a little more to see the result. Remember that we were in about 2000 elements, so we should have something like, you see, more than 800,000 elements. Now we have a very nice definition of the model, and for sure we will have a very accurate result, but probably we don't need this refinement. So let us go back again to the relative, because it is our base. Then we have a couple of parameters. One very interesting one is this radius of local refinement, because this refinement is it determines the size of a zone around one element that the user defines, within which the mesh is constructed with an enhancer properties that are defined by the user. I will abandon this study. I will create a new one. Because when I'm activating the study, I can say select elements for mesh concentration, okay, which is this case. So I will put this 1 millimeter as I had on the other condition, and now I can choose one element around where the refinement of the 5 units is will be used as reference. So you see that I have more finite elements, and the parameters, okay, are basically the same. I've chosen this line, and you see that around the line I have a bigger refinement. In this area, in this side here, I don't have anything. I've just said around this line, and I can pick a point instead of a line, so it's not a big deal. This is a very important parameter also. Then I have something called this global size propagation factor, and this is something that goes from 0 to 1. And we can define this as a control of the speed regarding the mesh variation from a reduced size to the general size. So 0, no saying on the opposite. 1, we have an evolution from reduced size to big size. 0, no evolution. So let us say 0. Let us calculate it again, and let us see the difference. You see, there is a refinement around the line, but then it goes straight to big elements without any evaluation, okay? And if we say something in the middle, we'll get something not good, but a little better, okay? So let us go back again to the 1, and we have something a little better than what we have. Then we have this global curvature size, and when we have this activated, we can call it the curvature ratio. This parameter enables the automatic processing of the curved surfaces. If I take this out, you should notice now, not in this particular case because I have the refinement, I will abandon the study. I will create a new study without this element here. So let us take the same parameters. Let us open this. So I have not pretty much refinement, but a little. If I take this completely out, we should have this, okay, very rough, okay. With this, we activate the rounding processor for these surfaces. And if I go smaller, this is the factor, this is the factor that increases or decreases the quality. So I had, let's say, 0.05. And we have this kind of structure in the opposition of what we had before, 0.15, so more rough. So this is a ratio. And then besides these two guys, we have also this parameter that it works together with this curvature size. And it's a kind of chord length. So we have a very nice graphic on our theoretical side. that shows this. So I think it may be also important for you to check that information. Then we have this optimization of the surface mesh. These are also parameters for these two options here: the surface mesh smoothing between 0 and 5, and the surface mesh proximity between 0 and 4. A brief description of what it does. This provides control over the process of generating an improved quality mesh, and this is divided or split in two actions. The first action, optimization, and then a smoothing. So by default I leave this on and I don't change these parameters, so these for the moment are less interesting and less important. We have this fixed self-intersection which we can activate, and this enables the checking of the mesh for self-intersection after the creation of the mesh, and if they are found, they will be fixed, if possible, by the system in automatic mode. And these mesh, these self-intersections appear if we have very coarse sizes, and if they are set in geometry that is highly curved. So very particular cases that we may have. Then we have a couple of parameters, this optimization of the volume mesh. So it is important because if we come to the view, we are working, we can consider surfaces or volumes, but this optimization helps to improve also the model. And this has to do with the maximum angle of the triangles for the surface mesh elements. So this is a medium value, so we can work a little out of this, but I would say that without having problems, I will not work around this parameter. This is considering these two stages when we are creating the mesh. This is a parameter that says to the system not to modify the mesh when it's trying to optimize the volume. Then we have a couple of parameters for defining this smallest corner angle, so we can have a definition out of this, and this defines the admissible range of angle values between a mesh element edges. So again, without having problems, I would say that these are very specific parameters for users that have a greater domain over these topics. Then we have also a very important parameter, which is the maximum number of elements. And in here we set the limitation on the total number of mesh elements. This is particularly important to prevent accidents on the creation of very large number of elements, especially nodes, which might significantly slow down both the generation of the mesh itself and the following solving. So we may have huge models, so we set a size which in this particular case is set for 10 million. And for the generics of the elements that we intend to work inside this module, I would say that for the majority it's enough and allow you to control this number of elements. Then we have this delay mesh generation. With this, we can save the user-defined parameters on the mesh generation without the creation of the mesh in the current moment. So it's also a detail. And fix intersections also here. When everything it is done, we can go and create the mesh. There are a couple of more parameters also that we can work around here. So one of these is on the View tab. We can specify the type of mesh rendering. When we choose the surface mesh, it's a lighter version and more fast of the model. When we have the volume rendering is shown for the entire mesh, including the portions within the interior of the module. The module's volume, sorry. This is slower, so in most of the cases, this is enough for what we need. Information. So we have statistics for what we have for the current mesh. So number of vertices and the volumetric elements, what we have, tetrahedrons, we have 226. And we have a couple of informations for the angles between the edges, maximum and minimum, and the volumes and so on. Okay, so this is merely information, but it can be useful at a certain level. Just making a conclusion out of this lesson. This mesh topic, it's truly important. Okay, it's fundamental to have accurate results and to have good performance on the calculations. Anyway, I think it's quite interesting to start the use of these and to get some knowledge going through some very basic bodies or elements from the CAD. We can try a couple of parameters, having a couple of simulations to see the differences, and it's a good learning area, and for sure it will quickly put all users to a very good level. You can see also all of these lessons, which I think have some good informations to explain some of the concepts. And besides, we have a set of videos where we show how to create and how to get results for a huge group of situations and different types of calculations, which for sure will help you also to replicate those commands and to understand what is possible to do with this T-FLEX analysis. Anyway, any support, any help you may need, anything less clear on this video, you can contact us, and we will give you all the necessary help about this and other topics that you may need.